Hello and welcome to Lecture 17 for the course ECE 252B, Computer Arithmetic, Spring 2020. This lecture covers Chapter 19 in the textbook as well as Chapter 20, with less detail from Chapter 20. Now, Chapter 19 is perhaps one of the most important chapters in our discussion. It deals with errors and error control. Basically, in this chapter, we develop an understanding of errors in floating point arithmetic, what causes such errors, and what we can do about controlling them. We can't totally eliminate errors in floating point arithmetic, but if we are aware of how they develop, we can come up with methods to minimize them or reduce the danger of errors in the results. Okay, so let's begin with a simple example. First of all, there are two sources of errors in floating point arithmetic that we need to understand so that we can counteract them. One source is representation error. Some numbers do not have an exact floating point representation. Of course, irrational numbers such as square root of 2 or pi don't have any finite representation, and therefore they don't have any floating point representation. But numbers such as 1/3 also do not have an exact floating point representation in either binary or decimal. Okay, they may have, for example, if we were using radix 3 arithmetic, then 1/3 would have an exact representation. But in radix 2 or radix 10, it does not. Okay, so some numbers basically do not have exact representations. And then the second source is arithmetic errors. Even if our numbers are exact, when we combine them using arithmetic operations, the result of that arithmetic operation may not be exact. And here's a simple example. Take the number 1 plus 2 to the minus 12. Let me switch to slideshow. Okay, so take 1 plus 2 to the minus 12. Okay, this is basically a number that is representable exactly because this is basically significant. The exponent will be 0. And the significand, this is the hidden 1. And this 2 to the minus 12 is a 1 in the 12th position after the radix point. Okay, so in single precision or short IEEE format, we have 23 positions. So of course, position 12, we can represent, we can put a 1 in position 12. But if we square this number, in other words, multiply it by itself, the exact result is given here. 1 plus 2 to the minus 11 plus 2 to the minus 24. And this number does not have an exact representation in IEEE short format. Again, this is the hidden 1. This is a 1 in position 11 after the radix point. This would be a 1 in position 24, but we have only 23 positions after the radix point in the short format. Okay, therefore we cannot represent that. If we chop that extra bit, we commit this much error, 2 to the minus 24 error. Or if we round up, we still have this much error. Okay, in chapter 1, which I did not cover as part of my lectures, there are a couple of examples of errors in arithmetic due to finite precision leading to disasters. These are documented disasters that have happened because of arithmetic errors, okay? So if you go back and study the one that deals with floating point arithmetic, it's quite interesting. So you should go back to chapter 1 and read about the disaster caused by errors in floating point arithmetic that were not properly analyzed or anticipated, and therefore they caused the destruction of some very expensive equipment, rockets. Okay, so here is a very simple example to get us started. Suppose I want to compute this expression 1 over 99 minus 1 over 100, and these are decimal numbers. And I'm going to represent both of them in a floating point format with 4 digits significant. Okay? So first, the exact result of this arithmetic operation is 1 over 9900. That can be easily verified. And 1 over 9900 with 4-digit floating point significant, and the single-digit signed exponent is this. This is not a binary number. This is decimal, which happens to have only digits 1 and 0. 1.010 is the significant, and the exponent is minus 4. And the error in this representation, basically, it's easy to see that the exact representations would be 1.0101010 all the way to infinity. But we have to chop at this point. We could have rounded, but I'm assuming chopping. So we chop to 3 decimals. And in doing so, the difference between this number and this exact number is roughly 10 to the minus 8. Or in relative terms, so that's the absolute error. In relative terms, the error is 0.01%. Okay? So let's go to representations of x and y. X is 1 over 99, which has this floating point representation. The error is 10 to the minus 6. It's still 0.01% in relative terms. Y is representable exactly in this format. So it's basically 1 times 10 to the minus 2. So there's no error in y, in representing y. And then if we compute the difference between these two floating point representations using the rules of floating point arithmetic. So in this chapter, when I use the subscript FP, that means we are doing this operation using the rules of floating point arithmetic. It's not a normal subtraction. It's not an exact subtraction. Okay, so we take the two numbers, the exponents are equal, so we just subtract the significant. The ones cancel out, so I get 0.01, and then I normalize, and I get 1 times 10 to the minus 4. Okay, so the floating point representations of x and y were obtained, and floating point subtraction was performed, and we got this result, 1 times 10 to the minus 4. Okay, and the error in this value is 10 to the minus 6, roughly 1%. So the error is much larger compared with representation errors in the operands. One of them is 0, one of them is 0.01%. And relative to the exact result that we obtained here, we obtained the exact result and then represented the exact result. Okay, there the error was also 0.01%, much smaller than what I get. So this basically shows us that floating point arithmetic introduces additional errors beyond what the representation error. So as I mentioned, there are two sources of errors. One is representation error, one is arithmetic errors. So both must be considered. In this case, the arithmetic operation introduced additional error compared with the representation errors. Okay, we'll see the sources of these errors and the dangers that we face if we don't properly consider the possibility of errors. Okay, in order to make our discussion precise, we are going to consider a floating point system, FLP, in radix R, p digits of precision, meaning that our significance have p digits after the radix point, and an approximation scheme that we choose. Examples of approximation schemes are chopping. So when a result has extra digits compared with what we can accommodate, we simply chop the extra digits. And so when you represent a value in floating point with the exponent e and the significand s sub fp, meaning the floating point significand, rather than the exact significand, we commit an error, relative error eta. In other words, what we represent is not x, but 1 plus eta times x. Eta is a very small number representing the relative error. Eta, of course, can be positive or negative, so this doesn't mean that the representation is always larger. It can be smaller than x if eta is negative. Okay? Now, when we chop results, eta is always negative. In other words, we always get a smaller value, and the range of the error is from 0 to r times ULP. So if you're using radix 2, up to 2 ULP in the negative direction. Okay? If we round, on the other hand, then the difference between the floating point significand and the exact significand that we could have had if we had unlimited precision is ULP over 2, but it can be positive or negative. And the relative error eta has a magnitude that is half as much as in chopping in the worst case. Okay, and we assume that the ideal arithmetic in this floating point system is to obtain infinite precision result and then chop round whatever approximation scheme we are using in order to represent that precise result in floating point representation. Okay, now real machines, of course, it's impractical to keep infinite precision during the computations. So real machines approximate this process by keeping a number of guard digits. So G in our notation is the number of guard digits. So if we keep 2 guard digits, it means we do all the intermediate calculations with 2 extra digits. And then at the end, we say chop the result to the appropriate width. Okay, so let's do some very simple analysis for floating point operations, starting with multiplication. So when we multiply two floating point numbers, xfp, so this is the floating point representation of x, multiplied using the rules of floating point arithmetic by the floating point representation of y, the result will have some relative error eta compared to the exact product of those two representations. So if these representations, let's say, are in IEEE short format, each of these will have 23 fractional bits. When we multiply them, there will be 46 fractional bits. We have to get rid of the extra bits, and that introduces some error. Okay, on the other hand, the XFP is itself an inexact representation of x. Let's say XFP is 1 plus sigma times x, and YFP is 1 plus tau times y. So sigma and tau are representation errors, and eta is arithmetic error in multiplication. If you multiply out these three parentheses and ignore the higher order terms, so remember I said that these numbers are small, eta, sigma, and tau are very small. So we can ignore the second order terms and this 1/3 order term. And therefore, the result is approximately 1 plus eta plus sigma plus tau times xy. In other words, the floating point product compared with the exact product has a relative error of eta plus sigma plus tau. So errors basically can amplify in the course of computation. We started with each operand having some error, 1 sigma, 1 tau, and then the product has this error. Notice, however, that these errors can be positive or negative. So basically, sometimes errors cancel out. But in the worst case, they're all in the same direction. So let's say they're all positive, and let's say they're all roughly the same. We have 3 times as much error. Okay, if all 3 terms are about the same, when we multiply 2 numbers, we have 3 times as much error in the product than we had in the original operands. Okay, analysis of division is similar. Again, the division operation introduces some error, but then x and y themselves have some error. And then I just basically expand 1 over 1 plus tau in this form. And then again, I ignore higher order terms, and I get this. So the floating point quotient or division result is related to the exact division result or quotient by this error. Okay, notice that the sign of tau is negative, but that's not really significant because tau itself can be negative. So the fact that we have negative here doesn't mean that this error will be smaller. It can still be as large as the error in multiplication depending on the sign of the 3 terms. So if eta and sigma are positive and tau is negative, then, and let's say magnitudes are roughly the same, we can have up to 3 times as much error in the worst case. Okay, now comes the interesting part. When we have addition, we do the same thing. So we add 2 floating point representation using the rules of floating point addition. Let's say x and y are both positive or have the same sign. Then this is the error in the addition process. Again, XFP itself is x plus sigma x. It has some error. YFP is y plus tau y. And then I can basically transform that expression into this one, which tells me that the error in the addition result relative to the exact sum is eta plus this term, if this term is small, okay? So under what condition is that term small? Well, if x and y have the same sign, if x and y are positive, let's say, and let's say sigma and tau are roughly the same, or I take the larger, so let's say sigma is the larger one, and then I replace tau with sigma, this only increases this fraction, so it basically gives me an upper bound on the error. And then sigma x plus sigma y divided by x plus y is sigma. So basically the error will be eta plus the larger of the sigma and tau. So it's still reasonably small. Let's say if these two are comparable, it's twice the error in the representation. Okay, so addition with operands of the same sign does not create any undue problem. It's pretty much like multiplication and division. However, when you do subtraction or addition of numbers with different signs, something very interesting happens. So here I have 1 plus eta xfp minus yfp, and again x fp is x plus sigma x. There's some error in representation. Yfp is y plus tau y. And then I sort of manipulate the expression to get this one. Superficially, this looks like what we had up there. So we may think, oh, no big deal. However, suppose x and y are fairly large numbers. But x minus y is a small number. This can happen, you know. You can have x equal to 1 million and y 999,999. So x and y are large, but the difference is small. So this is a small number. In the numerator, however, if tau is negative, this can be, let's say, sigma and tau are the same. They're both sigma. So I have sigma x, and tau is negative sigma. So I have sigma times x plus y. So this fraction is sigma times x plus y divided by x minus y. So sigma is multiplied by this fraction x plus y divided by x minus y, which is a very large number in the example that I told you. So if x and y are each about 1 million, x plus y is 2 million, and x minus y can be 1. So the error is significantly amplified. So instead of having sigma here in this term, which we had up here, we will have 2 million times sigma, okay? So floating point subtraction or floating point addition with operands of different signs can potentially introduce very large errors in the results. And this is really the source of many of the difficulties that we face in controlling errors in floating point arithmetic. This case of dealing with numbers that are fairly close to each other in magnitude, and then we subtract them. Not only this fraction over here is unbounded, it can be very large, depending on the ratio of x plus y divided by x minus y. This eta itself is also unbounded, so we are in a double whammy, so to speak. You know, we have two large sources of errors. Okay, this situation is known as cancellation error. Cancellation error when you subtract two values that are close to each other in magnitude, leading to the cancellation or disappearance of significant digits. Okay, let's take a numeric. So this is the formula from the previous slide. Let's take an example. Let's say you're doing radix 10 arithmetic with 6 significant digits, and we use no guard digit. We simply chop the results to the appropriate width. Now, if the x has the exact value 0.1 times 10 to the 3, okay, its floating point representation will be exact. I just chop the 3 extra zeros and get this representation with 6 digits of precision. Let's say y is this number times 10 to the 2. If I chop it to 6 digits, I get this value. Notice that these two numbers are very close. This one is 0.1 times 1,000. It's about 100. That's 100. Exactly 100. And this one is 99 point, because it's multiplied by 10 to the 2, 99.9999456. Okay, so the two numbers are very close to each other, although they have different exponents. The numbers, the magnitudes of the two numbers, very close. One is positive, one is negative. So x plus y, the exact sum of x plus y, we can compute, and is this. 0.544 times 10 to the minus 4. The exact sum of the floating point representation. So assume we didn't know the exact values of x and y, we were just given the floating point representations. The exact sum of these two values is 0.1 times 10 to the minus 3. Okay, so even without arithmetic errors, just because of the representation error, we are getting two vastly different numbers. 0.5 times 10 to the minus 4 versus 0.1 times 10 to the minus 3. If you write this as 10 to the minus 4, this will be 1. 1 times 10 to the minus 4. So the two values are vastly different because of that cancellation effect. Now, if I do floating point addition of the two representations, basically I have to shift this number to the right because its exponent is 1 less. So this 9 basically, remember I said I'm using chopping, so that 9 is basically dropped. And I get this value. So I have three values here. The exact sum of the floating point representations, and the floating point sum of the floating point representation. Vastly different numbers. This one let me see. Okay, I believe there may be an error here. So when I do the exact sum of the floating point representations, I actually do keep this digit that is shifted out, and the result should be different. Okay, I'll go back and take a look at this and make corrections if needed. At any rate, the relative error in this result, this is basically 10 to the minus 4, 0.1 times 10 to the minus 3, compared with the exact result up there, is 83.8%. Okay, definitely not acceptable as to have a result, computation result that has an error of 83.8%, roughly 84%. Okay, I think, sorry. Now we ignore the representation errors so as just to focus on the effect of eta, the arithmetic error. Okay, basically compare this result that I obtained with floating point arithmetic with the result that I would obtain with exact arithmetic and the floating point representations. The relative error will be 0. So apparently there's no error here. For some reason I thought there's an error. So the result of floating point arithmetic actually matches the result of exact arithmetic and the floating point representations. Okay. So a natural question is, if we want to perform floating point arithmetic computation using guard digits, in other words, carry extra digits of precision, how many do we need? It's a non-trivial question. How many do we need to guarantee some good error bounds? And this theorem answers the question. In the floating point system, radix r with p digits of precision and chopping with g guard digit as the approximation method. In other words, all intermediate results have g extra digits, and they're chopped beyond that. Okay, then the result of floating point addition is 1 plus eta times the exact sum of the floating point number. Remember, when plus has an FP subscript, means this is a floating point addition. When plus is just by itself, it means exact addition. So floating point operations, floating point addition compared with exact addition of floating point numbers has an error eta, and that eta is bounded by these two values, minus r to the minus p plus 1. So this is a fairly small number if precision is high. And on the positive side, r to the p minus g plus 2. Okay, so this theorem I'm not going to prove. It's a well-known theorem. So basically, if I keep just one guard digit, corollary to this theorem, one guard digit, replace g with 1, this will also be negative p plus 1. So the two positive and negative bounds match in magnitude. Therefore, if I chop all the intermediate results after keeping one guard digit, then the bound on arithmetic error is acceptable. Okay, remember we said there are two. In the previous example, the arithmetic error was actually 0, okay, for these specific numbers. But there was the representation error caused pretty significant errors. But with one guard digit, I'm guaranteed to have a good bound on the relative error resulting from the arithmetic operation. Of course, if I keep more guard digits, the error will be less, but one guard digit is all I need to have a reasonable error bound. Okay, now, it turns out that in floating point arithmetic, laws of algebra that we have come to expect do not hold, and this can be the source of many additional difficulties. For example, the most well-known example is the associative law of addition, meaning that if you have three numbers and you want to add them, it doesn't matter in normal algebra. If you add B to C first and then add A, or add A to B first and then add C. Addition is associative. In floating point, addition is not associative. You can get different results. So if A, B, and C are floating point numbers, you can get different results, vastly different results, if you first add A to B and then add C versus first adding B to C and then adding A. And this example basically shows why. Let's take three specific numbers, A, B, and C. Notice that A and B are fairly large in magnitude. Their exponent is 10 to the 5. C is fairly small, relatively speaking. Its exponent is 1, 10 to the 1. Furthermore, these two numbers are pretty close in magnitude. They have different signs, so we can expect that cancellation may lead to problems. Okay, so intuitively what happens if you first add B to C, this being a large number, this being a small number, small exponent, you basically shift this to the right and lose the digits of C as they are shifted to the right. And therefore C does not make much difference when you add it. So B plus C will be roughly equal to B. And then when you do this addition of A, then you get something close to 0. On the other hand, if you do A plus B first, the second version, you get a fairly small number. And that small number added to C, here C makes a big difference in the result. Because that small number, so here's the numerical example. If you do B plus C first, okay, you shift C so 1, 2, 3, 4, 1, 10 to the 5. That's A plus, so I'm doing B plus C first. Okay, when I shift this to the right, I get this value for the significant. Notice that value isn't much different from what I had up there. So C made a very small difference in the magnitude B plus C. And then when I add A, I get 0.2 times 10 to the 1. What happens if I do A plus B first? So here is A, here is B. The exponents are the same. I just do subtraction. And then I get a lot of leading zeros. I get basically 0, 0, 0, 0, 1. And then I shift to the left and adjust the exponent, and I get this number. So I got 0.2 times 10 to the 1 in the first version, and 0.24321 times 10 to the 1, which is very different. The results differ by more than 20%. Okay, and 20% is a very large error. Okay, so this is an elaboration on what happened in the example on the previous slide. When I compute S1 first, okay, the small value of C barely makes a dent, yielding a value A plus S1 that is not much affected by the value of C. On the other hand, if I compute A plus B first, S2, this sum, the result will be nearly zero, making the effect of C on the final sum more pronounced. So a byproduct of this is that, you know, the order of operations in floating point, if you are adding a list of numbers, the order of operation makes a difference. And therefore, if you have, let's say, an optimizing compiler that rearranges the terms in order to gain performance. So for example, when you try to access, let's say the computation is written as A plus B plus C, okay? The original form is this. Okay, but if you get maybe a page fault in accessing C or a cache miss, you may decide that it's better to do A plus B first. So the optimizing compiler basically does A plus B first and then add C. And by this change, this optimization in performance changes the result. So often in floating point computations, what people do, they turn off all optimizations by the compiler because they don't want terms to be rearranged and therefore the results to be affected from one run to another run, or from run on one machine to a run on a different machine. Now, unfortunately, guard digits do not help with these invalidated laws of algebra. They improve the situation, but they don't eliminate the problem. Okay, let's see why. So I'm taking the same example as before, but this time I keep 2 guard digits during the computations. And I do the computations. This version of the computation gives me this number, and the second version gives me this number. Okay, please go through these steps and make sure you understand how these are obtained. Now, even though this is better, the difference is much smaller than in the original version without guard digits. The error of about 0.1% is still too large for comfort. So guard digits do not eliminate the invalidation of laws of algebra. They just help improve the accuracy a little bit. Okay, sometimes, so if you do floating point arithmetic using IEEE standard, all the results are normalized. So when you get leading zeros or leading ones in negative numbers, you shift the value to the left to eliminate the leading zeros and adjust the exponent. One option is not to do that normalization. In other words, do unnormalized floating point arithmetic. Of course, you can't do this with IEEE standard, but you can basically do your own design and development. If you do that, then these two computations using B plus C first versus A plus B first lead to the same result. Not only do they lead to the same result, but also the result carries a sort of warning about loss of precision. So you see here that you have 4 leading zeros, then 2, and there are also, digits that have been eliminated because we didn't have room for them. Now those eliminated digits, given that this number is fairly small, become significant. So for example, if the next digit were 4, and we had to drop it because we didn't have room for it, this is a significant error, dropping 4. So basically dropping 0.4 ULP compared to 2 ULP, which is the number itself. Okay, so that's a big error. So when a number has a small number of, this is known as a significant digit. Leading zeros are not significant digits. Okay. So when you have a small number of significant digits, then that's a sign that you have lost precision in the course of computation. So that can be viewed as a sort of warning that this result cannot be trusted because it may contain a large error. Whereas if you normalize this and wrote this as 0.2, so 1, 2, 3, 4 shifts, times 10 to the 1, 0.20000 times 10 to the 1, you lose that warning because you have no idea whether those trailing zeros after 2 are basically part of an exact value or they were basically created as a result of left shift. But when the leading digits are zeros, then that's a warning sign about loss of precision. So here are some other examples of invalidated laws of algebra. I won't go through them in great detail. So the same invalidation of associativity applies to multiplication. It does matter when you multiply 3 numbers whether you do A times B first or B times C first. Cancellation law does not apply. Normal algebra, if you have A times B equal A times C, that implies B equal to C. But you can multiply a floating point number by 2 different floating point numbers and get the same result. Distributive law does not hold. So A times B plus C is not the same as A times B plus A times C. And finally, multiplication does not cancel division in general. If you divide B by A and then multiply by A, you don't necessarily get B. Okay? And this is something we have all experienced. If this is 1/3 and this is 3, so in a calculator, if you enter 1/3 and then multiply by 3, you may not get 1. On most calculators, actually, you do get 1 because they have guard digits. They have hidden digits internally. So 1/3, for example, let's say we have just 2 digits of precision. 1/3 is not represented as 0.33, but as 0.3333 if you have 2 guard digits. And then when you multiply that by 3, you get 0.9999. And then when you round it to 2 digits, you don't get 0.99, but you get 1. Okay? So those guard digits help protect us against this problem. Okay, so one remedy for this problem is to be careful about the algorithms we choose for computations. Different algorithms, different ways of deriving the same result can impact the final error, as we saw in the associativity and other laws of algebra that are violated. So here is basically example 19.3. We try to find the roots of the quadratic equation x squared plus 2bx plus c equal to 0. And we know from calculus that the result is minus b plus or minus d, where d is the square root of b squared minus c. So this is the formula that we know and routinely use to find the roots of a quadratic equation of this form. Here's the problem that we can run into. If b is a large number and c is a small number, b squared minus c will be approximately equal to b squared, and the square root of that will be approximately b. And then in the root that is negative b plus d, which is now almost equal to b, we have cancellation, and we get imprecision in the result. Okay? We can use this alternative formula in those cases. So it's pretty easy to prove that this formula is also correct, and the proof is shown here. So compute x instead of negative b plus or minus d, where d is the square root, as negative z divided by b plus or minus d, where d is that square root. Let's see what happens here if b is large and c is small. So b squared minus c will be roughly b squared, and the square root will be b. Okay, so b, this I'm doing for the root with the plus. The root with minus doesn't have any problems there. The root with the plus, you have b plus b, 2b. So you have c, which is a small number, divided by 2b, and that's a fairly small number, and it's much more accurate than if you had done it using the other equation. Okay, so just being aware that whenever you do addition of two floating point numbers with different signs, you have to be careful. We can rearrange the formula in that case, negative b plus d, by writing it as negative z divided by b plus d, and then that problem disappears. Okay, here's a second example. There are many examples. Over the years, people have come up with alternate formulations to be able to avoid these large errors. And this one basically has to do with computing the area of a triangle. Again, you may know that this formula gives the area of a triangle of side lengths A, B, and C, where S is half of the perimeter, so A plus B plus C over 2. So S is half of the perimeter, A, B, and C are the side length. You just plug in this formula, extract the square root, and that's your area. And most of the times this formula works well, but if you have what are known as needle-like triangles, a triangle that is very narrow, what happens is, let's say this longest side is A, okay? A plus B plus C over 2 will be very close to this, so this S will be very close to A, and you can get cancellation here, leading to errors, okay? This alternative formula, due to William Kahan, can be used for computing the area of a very narrow or needle-like triangle. It's very easy to prove the equivalence of this formula to that one, but this one avoids that situation. So A plus B plus C, meaning add B to C and then add A. The second term is A minus B, and so on. And it's provable that this formulation does not lead to large errors. Okay, so that was the second example. Use a different formula for computing the area of a triangle when the triangle is of this kind. Okay, now other than errors in individual floating point operations, we have the danger of error accumulation. This means that if you do a long sequence of computations, each one introducing a small error, then those errors in the worst case accumulate. Of course, remember I said that errors can be in the positive or negative direction. So sometimes errors actually cancel each other out. So statistically speaking, the error magnitude can be small on average because sometimes they cancel out. But the worst case analysis shows that all of those errors add up in every step of the calculation. So if you do many millions of steps in the calculation and you're unlucky that the errors are in the same direction, then you can get pretty poor results. Okay, so here's an example. Suppose you want to do inner product calculation. So a bunch of numbers, so the two vectors x and y are given, their corresponding elements are multiplied, and then they're added. If we do a regular multiply add operation, the multiplication generates the worst case ULP over 2 error. The addition of that product to the running total, another ULP over 2. So the worst case error for each of these terms is ULP. Now, if the vectors are 1024 elements long, then and all the errors happen to be worst case and in the same direction, you get up to 1024 ULP errors. And this is equivalent to losing 10 bits of precision. Roughly 1000 ULP is equivalent to losing 10 bits of precision. Of course, this is a worst case that may not occur, but you can count on errors actually canceling each other out. Okay, so what is the cure? Of course, if you have a single operation multiply add, okay, so instead of doing 2 floating point operations, you do just 1. So in each step, your error will be ULP over 2. That helps, but not much, because you still have 512 ULP. 9 bits of precision will be lost. Now, when I need high precision inner product calculation, a better way is to do the product, the multiply, keep the running total in double the precision. In other words, do not drop any bits of the product. Keep it in full precision and add it to the running total in full precision. Okay, so you do all 1024 steps without introducing any errors. And then at the very end, so each addition, there is a small error, but it's negligible. And multiplications do not introduce any round of error because you keep the full multiplication result. But each addition can result, remember the additions are also double width. So ULP squared over 2 is the worst case error in each addition. And 1024 times that, plus ULP over 2 in the final rounding of the result from double the precision to regular precision. So this number can be fairly small because if ULP, let's say, is to the minus 23, let's say, even short floating point number, to the minus 23 This will be 2 to the minus 46 divided by 2 to the minus 47. 2 to the minus 47 times 2 to the 10 is 2 to the minus 37. So this part is 2 to the minus 37, whereas this part is 2 to the minus 24. Okay, so this can be pretty much ignored, and therefore you have a fairly small error. You lose basically at most 1 bit of precision as opposed to 10 bits up there. Okay, William Kahan also introduced a floating point summation algorithm that tries to minimize errors when you add up a long list of floating point numbers. I won't go through this. You can study it on your own if you are interested. The key idea here is that a correction term is kept. So when you want to add two floating point numbers, or a bunch of floating point numbers, x0, x1, x2, and so on. So you start with the first number. In each step, you have a correction term from the previous iteration, C. You incorporate that correction term, and then whatever y you get, you add it to the running total, call it z, and then find the correction term for the next step by doing this. Now this calculation normally should, if everything was exact, should yield 0. See, z was assigned a value s plus y. So if you do z minus s and then minus y, the result should be 0. But this won't be 0. It will be a very small floating point number, which is the correction term that you keep around and you apply in the next step. And then the next step in term will generate a correction term. So those small values that are normally lost to right shift are kept and carried from one step to the next step. Okay, so this reduces error in adding a list of floating point numbers, but it comes with a performance penalty. So in each step you're adding one number, but instead of doing one floating point addition, you're actually doing 4 floating point additions. Here's 1, 2, 3, 4. So each iteration requires 4 floating point additions and some housekeeping operations. But it reduces the final error. Now, since Kahan's initial formulation of this problem, a lot of additional work has been done on accurate addition of a list of floating point numbers. And some of the references are at the end of the chapter. There are many other ways that you can do this. For example, you can avoid doing multiple floating point operations per iteration by sorting the numbers. Let's say from largest to smallest, and then adding them. This guarantees that numbers with almost equal magnitude will be added in each step. Another trick is to add positive numbers and then add negative numbers separately, and then do one subtraction at the very end in order to avoid multiple cancellations in the course of your summation. So there are many, many methods, more sophisticated methods than what I just mentioned for doing this, and there are papers that describe these methods. Okay, this section I'm gonna delete. As I do sections 19.5 and 19.6 so that I can cover a little bit from chapter 20 in the remaining time. Okay, so in chapter 20, first we talk about various ways of basically avoiding loss of precision. The ultimate, of course, is doing, exact arithmetic. Okay, that comes with a significant overhead, as I'll show you in a few minutes. We can make arithmetic highly precise to raise our confidence in the validity of the result through multiple or variable precision arithmetic. And finally, doing ordinary or high precision calculations while tracking potential error accumulations. So that at the end, when you obtain a result, you also have a bound on the error. So you will not be misled by a totally wrong result, given that you have a bound on the error. So if the bound is large, then you don't trust that result, and therefore you ignore it or you redo the calculation. Okay, so what is exact arithmetic? This continued fraction I'm going to skip. So, for example, you can represent numbers by rational approximations. So, for example, the fixed slash number system, which is so named because of its similarity to fixed point. So slash is basically in some implied position, and the number being represented by this format is p divided by q. So remember I mentioned the number 1/3. 1/3 has an exact representation in this format. You just put 1 where p is and 3 where q is, and you have the exact representation of 1/3. Okay, so if you multiply 1/3 by 1/3, you get 1/9, still represented exactly. Now the problem with this is that as you multiply or add rational numbers, fractions in this way, the numbers p and q can get large, thereby exceeding the capacity that you have there. Of course, you can try to simplify. So for example, if you get 3 9s in the course of some computation, you can say, okay, 3 9s, I divide both of them by 3 and make it into 1/3 to avoid increasing the magnitudes of p and q. But that simplification is non-trivial and is computationally intensive, and therefore it creates much overhead. So this scheme has not been widely used in practice. It has its applications, but it's not a commonly used method. We can also have floating slash number system, where the location of the slash is not fixed, but determined by this parameter m, which is similar to the exponent in floating point number. So this parameter m basically says that the slash is m bits from the end. This allows you a trade-off. So if you have a large integer, so q is basically 1, you don't need to devote a lot of bits to q and make it go to waste. On the other hand, if p is small and q is large, you can devote more bits to q by changing this value m. Okay, this makes calculations even more difficult. You still have the same problems as fixed slash, but some additional problems arising from this variable position of the slash. So I mentioned these two examples just to let you know that there do exist formats, number representation formats, for exact arithmetic. Okay, we can also do multi-precision arithmetic. So if you are dealing with large integers, for example, you can devote multiple machine words to these numbers. And then you have to program addition of such numbers. So the machine itself has an adder for just words, But if your numbers take up 4 words, you have to develop addition, multiplication, and other algorithms, or use ready-made packages that are available for such multi-precision arithmetic. We can do a similar thing for floating point, perhaps put the exponent in a separate word, and then the significand in several words, and again, you have to develop algorithms for various arithmetic operations. For example, if this is these are significands of two floating point numbers in multiple precision, 4 words. Then when you want to add, you have to shift one of them. And then you have to develop an algorithm for floating point addition with shifting. And then you find the result. And then you have to obtain from these extra bits of y that were shifted out the guard, round, and sticky bits in order to be able to properly round this value. Okay, so that's one idea. You can increase the precision by using multi-precision arithmetic. There is this very interesting package, helpful package, available at this website. You can download it for free and learn about it on this website, that represents each floating point number using 2 floating point numbers in order to increase its precision. So in this example, x, which has a lot of precision, is broken down into 2 parts, the high part, which is this number, and the low part, which is this number. Notice that the difference between the exponents is 53. This means that x actually represents this number. So you have to right shift this by 53 bits. And so basically you have a doubly wide number represented as 2 ordinary double precision floating point numbers. Okay, so you represent your numbers in this way. It takes up, of course, 2 times as much storage, but then you have the higher precision. And then if you want to do addition, the algorithm takes many steps in order to make sure that you get the correct result. So each of the 2 numbers is represented in this form, but then the exponents may be different, and then one of them has to be shifted. So the algorithm is quite involved, but the package for doing those operations is available to you if you want to use it. Of course, performance will be pretty low because of those complex operations, but one application of this type of extra precision is checking the error proneness of some algorithm. So if you're doing a double precision computation, you have a program, you run the same calculation with quad precision to sort of check to make sure that the result of this quad precision is not much different than the double precision. So you do this only a few times for checking. So performance being low may not be that big a deal, but then you run your program after you make sure that its error characteristics are reasonable using just ordinary double precision or long floating point, okay? So this scheme is used only a few times for verifying the precision of your algorithm. Okay. Variable precision is the same idea, except that the precision is not fixed. You add words as the need arises. Now, one of the most interesting topics in this chapter is the use of interval arithmetic. Now, interval arithmetic has been around since the 1960s. It's not a new idea, but lately it has been brought to the forefront because of the development of new techniques for doing interval arithmetic, and also hardware becoming a lot cheaper, and therefore making the overhead of interval arithmetic acceptable. So what is interval arithmetic? So let me skip some of these slides. In interval arithmetic, each number is represented by a lower bound and upper bound. So for example, whenever you have a number that does not have an exact floating point representation, you use the interval consisting of the smaller floating point number just below your number and the larger floating point number just above. And this notation indicates that my number is in this range. Okay? This is the lower bound for the number. This is the upper bound. And if there's a second number with corresponding lower and upper bounds, you can add these two numbers by adding the lower bounds to get the lower bound of the sum and adding the upper bounds to get the upper bound of the sum. Similarly, there are formulas for subtraction, multiplication, and division. Okay, so I won't go into a lot of detail. So basically now you know that your sum is in this interval. You don't know the exact sum, but you have a lower bound for it and you have an upper bound for it. Okay, so if you take the midpoint of this interval as your result, so suppose this is the end of your calculation and you want to output this result, you take the midpoint of this interval, round it if needed, and then also half of the width of that interval will be your error bound. So you not only have a final result, but you have a bound on the error that helps you basically evaluate the accuracy of your result. Now, one problem with interval arithmetic, and one of the things that limited its use early on, is that these intervals tend to grow wider as you do more and more calculation. Suppose that the width of this interval is 1. Let's say, just as a toy example, x is in the range 1 to 2. Y is in the range 1 to 2. Then x plus y is in the range 2 to 4. So the width of the interval basically doubled as a result of this addition. Now you can imagine if you perform many thousands or millions of computations, each time your interval will get wider to the extent that after a while the interval doesn't provide any useful information. It's so wide that basically you have no idea what the accurate result is. But even those wide intervals still provide an error bound, okay? So they're useful in that sense that you don't know what the result is, but you're also aware not to use that value midpoint of the interval because it has a large error. Okay, so as I mentioned, in recent years, a lot of new results have been developed for interval arithmetic. And I won't go through any of the rest of this description. For example, we have the interval Newton method, which we referred to earlier as the Newton-Raphson method for finding the root of an equation. So you have the interval version of that. If you know the root is in this interval initially, then you use the interval Newton's method to refine that interval. So I0 is the initial interval. I1 is the next interval, which is smaller. And eventually, after many steps of refinement, this interval becomes very small, and that's basically your estimate for the root of the equation. Laws of algebra also do not apply in interval arithmetic. So, for example, if x, y, and z are interval variables, if you do this calculation, first add y and z and then multiply by x versus x times y plus x times z, you can get totally different result intervals. Okay, so it doesn't matter which one you use, and one may be more precise, lead to narrower interval than the other one. Okay, so let me stop at this point, and this ends our discussion of floating point arithmetic, or real number arithmetic, and associated errors and how to estimate the errors and deal with them, try to reduce them. Okay, we have 2 more lectures left in the course. One lecture, the next one, is on square rooting algorithms, and the last lecture is on function evaluation, notably the Cordic method, which is again an old method that is nowadays used in electronic calculators for low complexity evaluation of elementary functions. A scientific calculator has sine, cosine, square root, exponentiation, a lot of functions of interest. And it turns out that all of those functions can be evaluated by the low complexity Cordic method that we'll talk in the last lecture of the course. Now, I will record the next lecture soon, but bear in mind that Monday of next week is Memorial Day observance. So this coming week we have just one lecture, which is this one. And the other 2 lectures will be for the following week, but I'll record them much earlier and post them to the course website. Okay? See you in the next lecture. Bye.